Welcome to Training Module 16.2, Rotating Solid Carbide Application. I'm your trainer, Edwin Tunney, Training and Technical Specialist for Horn USA Incorporated. So before we get too far along, let's talk about how to assemble the tools. So the DG takes some assembly. So the first thing you want to do when assembling the DG tool is to clean and inspect all the mating surfaces. So this tool has a run out of around 15 micron. So you want to make sure that you don't lose any of that to dirt or debris. So you clean the interface, clean the taper here, and clean the inside, blow it out with compressed air, and clean the shank as well. The next step, you're going to want to insert into whatever holder system you're using. If you're using a Farion collet system or using a roll mill chuck, whatever the case is, these are cylindrical shanks. So you're going to want to insert that in and make sure with all cylindrical systems, you really want at least 2 times the diameter in clamping length for the best performance. Obviously, if you have to stick out just a little bit further, then you make that happen. But in general, a general rule of thumb for solid tools and the clamping length, you want 2 times the diameter. The next step you want to take is you use the proper clamping wrench. These are available through Horn, and you want to torque this tool down after you've tightened this up. You want to use this wrench flat and torque it all the way down. You do want contact. You don't want to leave a gap like you would with the mini milling system or any of the Horn systems where you need to leave a little clearance, but you want to tighten that all the way down and tighten it to a recommended torque. So for the different system sizes, so the DG has 4 different system sizes, has a different wrench, and you can either use a combination wrench or you can use the torque limiting, the clamping wrench, and you use a torque wrench. All of those available through Horn, or you can get the clamping wrench of your choosing. It just has to match the wrench size 8, 10, 13, or 17 respectively. We do have a combination wrench as well in case you want to, if you have multiple sizes. This one's a 10 and 12 or a 16 and 20, and that relates to the system size. So the DG10, the 12, 16, and 20. And you can use that to loosen the tool or just snug it up before you use the torque limiting wrench. Once everything is assembled, you want to make sure that you have face contact and taper contact. So you're going to tighten it all the way down. You really want to target a run out of 20 micron plus or minus 0.8 of total run out to get the best performance out of the tool. And different holding systems with solid carbide or the DG, depending on what you're using. Just as a review, you have Weldon systems, collet systems, hydraulic, as well as shrink fit. So with Weldon's, you have lower end on the run out side. The performance is lower end because of the run out, but the security of those systems is pretty high. Since a lot of times you're dealing with a Weldon flat, and so the tool pull out is minimized. Generally, you're looking at around 15 micron of run out with a Weldon system, and that's with a new system. So if you have old worn out Weldons, you really want to inspect those and really go for a new good system when you're dealing with solid carbide. because you're going to get the best productivity out of your investment. Weldons tend to be on the lower end as far as cost. So that's one reason they're used in many cases, but they're really, security wise, they're good. Performance though, they're really on the low end of things. Collet systems have come a long way. For instance, we offer the Farion system, which has extremely good runout, which is what you're looking for, as well as good clamping force of the end mill. So with a collet system, a modern collet system like the Farion system, you're maximizing the runout, thus the performance of the tool, and you have really good security. For instance, you can get specific sizes of Farion WD collets that have a retention nub that holds the end mill in and prevents it from creeping or pulling out of the tool. They generally tend to be lower end of cost wise. There's no real specialty equipment you need to buy with collet systems. Hydraulic system, I would strongly recommend on hydraulic. They're very good on runout and they're really good on performance, but security wise, I would only use those for profiling, finishing on end mills. I wouldn't use them for roughing. They generally have problems in pulling out, the end mill pulling out of the tool. So you use these more for drilling, but you can use them in a finishing situation. Because it's a different technology, it's a little more expensive than the collet system. And the last system, Shrink Fit, has very good runout, very high performance, and very good security, but they tend to be pretty pricey. You can use those for slotting and profiling that tend to hold the end mill very well. One thing you have to worry about though is, you know, the age and the number of times that this has been heat shrinked in, because over time you lose accuracy and clamping force with these systems. They tend to be a little more finicky also on the technical side, and that you have to use the right cycle and the right amount of heat for the right amount of time in order to properly unshrink and shrink the tools. Another thing to understand is the tolerances of your shanks. When you have a more precise shank, you generally have a better performance of the tool. So for instance, the DP series of end mills, those are all H5 on the shank, as well as the DS, the DC, and the DG. So that gives you better clamping force. And for instance, an H5 tolerance, if you take if you took a diameter of 6 to 10 millimeter, typical like a 1/4 inch to a 3/8 end mill size, then you're looking at on the upper tolerance, it's a plus nothing, and on the minus, it's the worst it's going to get is a -6 micron. So that's roughly a little less than 3/10. So pay attention to your shanks. That's going to give you a better clamping force and better precision of the system. And the reason you want all that precision in the system is basically the cutting section. So each tool has a limit, if you will, on the cutting section it can take. And when you vary that a lot because of runout, you really put a lot of risk into the process. So for instance, if you have a feed per tooth of 0.08 millimeter per tooth or 0.003 inch per tooth on a end mill, and your feed is designed at that feed. If you have a 3-micron run out, you have less than 5% error of that feed. So your tooth is only taking within 5% error of that 3/1000ths. So you can go on the upper end of the feed without increased risk of taking too big of a section and chipping your end mill. So on the other side of that, if you have a lot of run out, your feed per tooth can vary quite a bit. So if you have 15 micron of run out, you can have 20% error in your cutting, your effective feed per tooth. So always be aware of that when you're selecting both the end mill and the back end system to hold the end mill. Is run out is super critical to the process. So getting the best surface finish out of the tool means a lot of things. First, the spindle needs to be properly aligned with the proper run out. So spindle maintenance is very important if you're doing a lot of solid carbide end mill, a lot of solid carbide machining. The holder quality also, you want to really target less than 5 micron, and then tool and shank accuracy. So the entire stack up of the system, you really want to get within sort of less than 20 micron or 0.8 total run out to get the best out of the system. Get a drink of water. Questions so far?
Not yet.
Okay. All right. So one of the big influences of surface finish also is the cutting force and how much the tool is deflecting each time it passes through the material and the next flute is engaged. So use proper cutting speed. So cutting speed is going to help you. You want to make sure that you're not running too low of a speed. So surface finish can be affected when you have built up edge on the cutting tool, and built up edge is caused from low cutting speed, and sometimes using improper geometry of the tool, too dull or too negative of a tool in a material, for instance. But a lot of times proper cutting speed will solve any issues with built up edge, and then you won't try to machine with that material deposited right on the cutting edge. Imagine, if you will, when you cut a cardboard box with a razor knife, and it has that cardboard kind of wraps around the edge, how much more difficult that becomes to cut with it. So same concept with cutting tools and material deposited right on the cutting edge. The feed per tooth and the deflective forces are linear. So what that means, if you double the feed of a tool, you are effectively doubling that deflection, or you can double the deflection force. So it's a linear relationship. Now the curve might be more or less steep depending on the tool and the geometry, but from the lowest feed to the highest feed, you will increase by some amount, because that is a linear relationship. So if you want to reduce chatter and vibration, common sense, you just reduce your cutting section or your feed. And also think about feeding below the edge preparation, because that does have an effect on the vibration as well. So if your edge prep is maybe 5/10 of an inch, you want to make sure that your feed is above that edge prep. So you've seen, I think this chart maybe before, tend to be surface finish tends to get better in some situations when you use a variable helix. So a variable helix, essentially you're fly cutting with the tool because one of those flutes is sticking out just slightly more than the other. So that flute acts like a wiper, and it wipes that surface and gives you a really clean finish. All these will produce a good finish depending on, of course, the parameters. But as you move to a more a steeper helix, or from a 50-degree helix to a 30-degree helix, your surface finish is going to change dramatically. Another thing to think about, and this works especially for thin wall components, is to follow an 8-to-1 rule. So what the 8-to-1 rule is, when you're finishing a thin wall, you don't want to take a cutting depth more than 8 times your thickness here. So a 1.5 millimeter thick wall the max AP should be 12 millimeter. So in order to go past that, you want to make sure your cutting section should be such that you're not exceeding 8 times. So it's effectively keeping everything below 8 times that ratio. And also think about the process on thin wall stuff. The first thing is always finish the wall tops first. So don't ever machine the walls to finish size and then try to go back and clean up the top of the part. You want to bring the top of the part to size, whatever that is, and then work on the rest of the walls. So you can see the process here by where you go from pass 2 to 3, and you're staggering, you're staying within the 8-to-1, but you're staggering the dimension here. So at 2, then you increase to 3, then 4, then before you go any further down the wall, you start back again and you go to your semi-finished pass 5, 6, 7, 8, 9. And then you start working on this again, 10, 11. You stop short of the floor. So for the best finish on the part and the best dimensionals, you don't want to machine the floor of the part and the wall at the same time. You can rough these at the same time, but as far as finishing, you want to make sure that you leave that for the very last. So you'll clean this up when you're doing the floor, and you'll do your final touch to the wall. So you can see, I think another name for this also is a waterline machining. So you're just staggering your passes and you're maintaining the maximum cross section of the part as you're moving down the component. Another topic for that pertains to solid milling that's very important is chip thickness. So as you can see, when you have 50% of the tool engaged, so this is a top view of the end mill cutting a section. When you have 50% of the tool engaged, the average chip thickness really is pretty close to the feed. It's pretty close to the feed per tooth. As you decrease your engagement, you go from now to 25%. The thickness, or the median chip thickness, is equal to the feed per tooth times 0.5. And then also, if you go half of that again, your median chip thickness is your feed times 0.35. And then if you go down to 6.25% of diameter, it's 0.25. So the way you can leverage that is materials and a cutting edge, whatever the geometry of the tool, they have a median chip thickness that the tool will sustain. So for a long tool life, it will retain, let's say 3/1000 chip thickness. You won't break the edge down, and you'll cut cleanly through the material. If you go 4/1000 median chip thickness on a certain materials or a geometry, then your tool life starts to degrade. So using medium chip thickness and your chip thinning, you can go much higher feed rates and still have productive tool life. So long tool life where you're not changing end mills out very often. One thing to note is the formula is only valid when it's less than 50% of the diameter. So once you go more than 50% of the diameter, this formula to calculate what your chip thickness is doesn't work anymore. And just to review that, I'm sure many people have seen this before. It's the feed per tooth times the square root of the width of cut divided by the diameter. So keep all your units the same, whether you're inch or your metric. So in inches, your chip thickness, your median chip thickness in inches is equal to your depth of cut, your radial depth of cut or width of cut in inches divided by your diameter in inches, and then square that. Make sure your feet per tooth is also in inches. If you're on the metric side, it's millimeter per tooth times the AE or radial engagement in millimeter and your diameter in millimeter. So the square root of that. So very easy formula. I think well used in the all along the industry. So just a refresher. If you don't want to use that formula, you can just use a factor, and that's given by many manufacturers in a table format. But if you want adjusted feed, how much more you can increase depending on what your radial engagement is, you just multiply the feed times that AE factor, which is the feed per tooth times 1, that's for 50%. 40% is 1.02, 30% is 1.09, 25% 1.15, 10% is 1.66, and 5% is 2.29. So depending on the situation, if you're only 5% engaged with the tool, you can actually go more than 2 times on the feed, on the book feed for a given tool, and still maintain that same chip thickness. All right. So the next topic is arc of contact. So arc of contact is extremely important in all solid end milling, but it's also more important if you're dealing with a heat resistant alloy. So titanium or nickel alloys, this angle of engagement is very important. If you want to figure out what your angle of engagement is for a specific width of cut or AE, how much you're engaged in the material, you can do it with this formula. And it's basically the angle of engagement is equal to the inverse cosine of the radius minus AE over the radius. And you can take that angle of engagement is in radians. So that's very, very important point. That's in radians and not degrees. But you take the R, the radius of the tool. So that's the diameter of the tool times 0.5. And then your AE is your engagement. In this instance, I'm using millimeters, but you just replace inches wherever you have millimeters and you get the same result. The formula is valid up to 180 degrees, so full slotting. And if you want to convert the radians to degrees, you just take the radians times 180 over pi, and that'll give you the angle here in degrees rather than radians. Another special cutting calculation that needs to be made is when you're using round tools. So if you have a ball nose end mill, it's kind of where it comes in with respect to solid carbide. You can also adapt this to a button cutter with round inserts. But essentially, the effective cutting diameter should be calculated so that you get the proper cutting speed and the proper RPM of the tool. So the formula here, diameter effective, because you first have to figure out what your effective diameter is 2 times the square root of the depth of cut times the diameter minus the depth of cut. And that will give you the effective cutting diameter. So you can see here from the diagram what we're talking about. What is the diameter across the tool where you're actually making contact? You can then take that result and plug it into a modified speed formula where you say the cutting speed times 1,000 divided by the pi, divided by pi times the diameter effective, which will give you the proper RPM for this tool at that depth. If you vary the depth a lot with a ball nose tool for a specific reason, then you can either adjust the RPM based on that depth, or just take the average of all your depths and use that for the calculation of your effective cutting diameter. So in this formula as well, if you want to do this in inches, you just multiply by 12 instead of 1,000. It's just a conversion from meters to millimeters, getting all the units in the same order. So very effective formula at producing not only more productivity, because generally you're a smaller diameter, which means that your RPM should be a little higher, and thus your linear feed rate is going to be higher, and then not having built up edge and all kinds of issues from low speed. The other consideration that you can have is with round tools, you can also make use of chip thinning. So your median chip thickness or your average chip thickness can be calculated based on the depth of cut and the radius of the tool. So your median chip thickness is equal to the feed that you're taking. So your feed per tooth times the radius of the tool minus the radius of the tool squared minus the radius minus AP, all of that squared over the radius. All that to say that you can go faster if, depending on the depth of this tool, you can go a little bit faster because your chip thickness hasn't been reached yet. Another special consideration for round tools, for round ball nose end mills, is as you move towards the center of the tool, your rotation approaches zero. So a lot of times you'll find with ball nose that the center can be drug out and damaged, and you have plenty of life left on the tool out here. And it's just because this isn't really rotating at the very dead center. It's not rotating at all. But as you move out, the rotation increases, but you tend to be very low cutting speed towards the center, and you're dragging the tool. To counteract that, you can tilt the tool. If you have a 5-axis machine, you can tilt the tool so that your center zero rotation isn't dragging. So you're giving it a little clearance. So when you do that, you also change the effective cutting diameter, which you can calculate from this formula. Effective diameter is the diameter times the sine of the tilt angle plus the inverse cosine of the diameter minus 2 times the AP divided by the diameter. So that gives you your effective diameter. You can then recalculate your RPM based on the cutting speed that you're using this formula. The next topic to talk about is corner strategies. Using an end mill, even one standard size smaller, dramatically reduces the arc of contact. So your arc of contact is critical to your tool life. So for instance, if you have a 16 millimeter radius in a corner, then you can use a 12 millimeter tool, and that's going to reduce the amount of contact of that tool, and it's going to reduce heat of that process and keep your tool life a little bit longer. You should always reduce on corners. You should never drive straight into a corner and then change direction. That's very hard on any carbide tool, let alone solid carbide. You really always want to drive a radius in a corner. So always drive a radius. And the reason is you're keeping sort of a constant acceleration, and you don't have a snapback of the tool and friction between the tool and the material. If you've ever watched something machining, you'll know that as you're putting pressure on the spindle and the tool, it's not going to bend the carbide so much, but it's going to bend the entire system. So it's trying to pull the holder out of the spindle, and it's slightly bending that and putting pressure in one direction. Well, if you're going in a line here and you stop that acceleration, it's going to try to keep going, and you end up getting wrap around the tool, as well as that the forces and friction from that deflection. Another strategy for corners is to do a corner pick out with a different tool. So if you're able to do it, you can go in with an even smaller tool and you can pick out the corner. So you might enter on a 30-degree path, you drive a radius, and then you come out. And the only objective here is to remove the material from the corner. So this is especially helpful if you're machining titanium or nickel alloy or any difficult materials, is that the corners really wreck your tool a lot and rob tool life. So by using a sacrificial tool, a smaller one, to pick out the corner, you leave a nice exit and entry for your main finisher or roughing tool, semi-finishing tool. High feed tools, as we have, are a good option for that because you're just making a little path here, a very short path, but at higher feed rates. so you can get that corner cleaned for the subsequent operations. You can see here the stock left from that corner clean out. So you use the 10 millimeter to clean it out, and you use a 12 millimeter. You have a really soft exit from the cut, so not a lot of spring back or deflection. And then you enter into the back into the material in a very soft way. So minimizes also the tool wrap. So you don't have a large arc of contact and a lot of heat building up in the corners. Another sort of common sense approach too, as well, when you're dealing in solid carbide, is to try different paths. So one pocketing strategy that you can use, and this is a part of a lot of CAD software where you can spiral out. So spiral milling is very helpful at reducing damage to the tool from deflection. So if you have a long stick out of the tool, you can use a spiral milling. It's very soft because you're changing directions, but you're not doing it abruptly. And you spiral out. Even in roughing this pattern, obviously pockets are not all square. There's a lot of different shapes, but you can remove most of the material this way and have a still productive, but also easy on the end mills. And so improve your productivity and reduce the number of tool changes. Another strategy in pocketing with solid carbide too is avoid interrupted cutting. You want to avoid going over drilled holes. You want to drill the holes last because that interruption can cause some damage to the tool. Keep the tools moving. You want to keep the tool pressure on, and don't abruptly change direction because that's where you get tool wrapping and chipping. Don't do linear slotting with more than 4 flutes. I know there's a lot of 5-flute tools out there that say they can do slotting, but it's been my experience that you'll end up recutting chips. It's really better to use a trochoidal process with more flutes if that's the case. If you have a 5-8 flute tool, use trochoidal process to clear out slots. And don't Z-axis plunge with more than 2 flutes. It's not a good process anyway. Really more efficient to open up a hole and then drop your end mill in and do your machining. And on high-speed machining, you really want to get the most out of it. Don't do high-speed machining with less than 5 flutes. If you're only engaged 5 or 10%, it doesn't make sense to only have 3 or 4 flutes. Add another flute in and get a more linear feed rate, more inches per minute out of the process. Entry and exit paths are another clincher, maybe for people new to using solid carbide. Entry and exit, always be progressive with that. Enter in soft, use the arc in and also arc out. And that's going to help you avoid these surface defects where the end mill grabs and pushes into the material. Make sure to always soft entry in and soft entry out. And I mentioned this before, but I want to mention it again. When you're finishing, finish the wall and then do the floor. Don't do both at the same time. You have a radius here, and depending on the size of that radius, you might push off and get a worse surface finish. So always try to stop above the radius of the system of the component. Do the wall, do it all the way to maybe a spring pass, and then finish the bottom of your part with that finish pass. So don't try to do both at the same time. Be careful in solid. A common problem, especially with S group materials, is heat affected zones. So a heat effective zone is a change in the phase of the material. It's a layer that forms, and it's really damaging to your tool. So be very careful to not create these heat affected zones when using end mills. One way you can create these zones is using very high cutting speed, or too high of a cutting section and cutting speed for the material. Another way is using too low of a speed, where you're possibly you have built up edge, and you're cutting with a dull tool, and that leads to another, which is using dull tooling. So always keep an eye on your tools to make sure they're good and sharp when you're machining titanium or nickel alloys, because that will create those heat affected zones. Taking too many spring passes also does that as well. So if you just keep running over the material, you're building in that heat. You're rubbing rather than cutting, and you can cause heat affected zones, which, if you have subsequent processes, it can damage your tool. So just to sort of bring that point home, don't run feeds below the edge preparation. Don't take excessive finish passes. Don't run speeds outside the correct range. So don't, you can use high-speed machining on titanium. It's used very widely, but just don't have ridiculously high speeds. Do use a sharp end mill. Follow the 8-to-1 rule. Use the correct cutting speeds and feeds. Assure the coolant, so that's one that wasn't mentioned already. Make sure the coolant is applied for the duration of the cycle. So watch your, if you're using external coolant, watch that your part is not blocking coolant in any part of that process. If you're putting coolant on it, you want to keep that constant flow. And when you use high-speed milling, use that lower radial depth of cut, because that's not going to generate as much temperature, and temperature is really the culprit and what causes those heat affected zones. Temperature and work hardening, or putting stress in the material. Cutting condition wise, I just wanted to, I'm not going to go over every cutting condition for through the new Horn catalog, but I just want to make sure that it's clear a few points. First, when you're talking about conventional milling here, I think that's a little bit of a difference in translation. It's just standard milling. So standard milling, not conventional, in the sense that conventional and climb milling. With solid carbide, or really most indexable, climb milling is going to be what you use, where you're running thick to thin chip. Conventional milling in this chart doesn't mean what you would run for conventional milling. You're always going to climb mill. This is more or less a different way to say standard milling. So where you're cutting, profiling, or contouring with the tool. So also you can see that a bigger section here, that's the cutting speed for roughing. And then when you see the profile here, it's the cutting speed for finishing. You also have an option for high-speed milling. So if you're using a high-speed milling process, you can use the speeds listed here, one for roughing, one for finishing. So just keep that in mind. There's also some indication here on the cutting parameters. You can see they use the same symbology here. That's for roughing, and this is for finishing. And then you have a feed per tooth for roughing. You have a feed per tooth for finishing. And your AE, your width of cut, is given for roughing. Your width of cut is given for finishing. And your AP is depth of cut. Depth of cut for roughing and depth of cut for finishing. All right, thanks for joining us. Don't forget to subscribe so you get alerts when we post new videos. Thanks and have a great day.